Hi guys, welcome to the today's session of design and analysis of algorithms. In this session, we are going to discuss about one more application of dynamic programming. It is nothing but optimal binary search trees. So for knowing about optimal binary search trees, first you need to know what is a binary tree, what is a binary search tree, and after that, what is an optimal binary search tree. How to find optimal binary search trees for the given case using dynamic programming. Right. So first we are going to see a binary tree. What is a binary tree? A binary tree is a hierarchical data structure in which each node has at most 2 children. Okay. So each node is having maximum of 2 children. That is, a node may have 0 children or 1 children or 2 children, not more than that. If a node is having at most 2 children, then we can call it as a binary tree. So here you can see the example. This node is having 2 childs. One is left child and other is right child. This node is also having 2 childs. This node is also having 2 childs. This is also having 2 childs. This is also having 2 childs. This is having 1 child. This is also having 1 child. And all these are having 0 childs. Right. So every node is having maximum of 2 childs. That is either 0 childs or 1 child or 2 childs. Then we can call that as a binary tree. Right. Now, what is binary search tree? So binary search tree is a binary tree and that should satisfy some properties. Those properties are: the left subtree of node always contain nodes with keys less than nodes key. Right subtree of a node contains always nodes greater than its key. And both right and left subtree should also become binary search tree. Right. Now here you can see. First of all, here this is the example for binary search tree. First of all, for becoming this as a binary search tree, it should be a binary tree. Now first to see that whether it is a binary tree or not. This is having 2 childs. This is having 2 childs. This is having 2 childs. This is having 1. This is having 1. These 3 are having 0. This is also having 0 children. So at most 2 childs are there. So that's why it is a binary tree. Now the keys in the left subtree must be less than the parent or root. Now let us see. Here if you observe, the keys which are present in the left subtree 3, 6, 7, 1, 4 are less than the root node. And the keys which are present in the right subtree are greater than this node. Let us see. 10, 14, 13, which are greater than this node. Right. So this property is satisfied. And left and right subtree should also be binary search tree. Now if you observe this left subtree, now here this itself is a binary tree, and left nodes are less than it and right nodes are greater than it. Right. So this is also a binary search tree. If you are taking this one, this itself is a binary tree and right subtree is greater than it and left subtree is less than it. So this is also a binary search tree. So this property is also satisfied. So that's why we can say that this entirely is a binary search tree. Now, what is optimal binary search tree? Now here you can see that for the given number of keys, we can construct a number of binary search trees. Let us see. So if I given 2 keys or 3 keys, how to construct it? Here the 3 keys given are 10, 12, 20. So if I given 3 keys are 10, 12, 20. Now with these 3 keys, what the binary search trees that I can draw? I can take 10 as the root node, 12 is its right child and 20 is its right child. Or I can take 12 as the root node, 10 is its left and 20 is its right. Now I can take 20 as the root node, 12 is its left child and 10 is its left child. Now I can take 10 as the root node and 20 its right child. Now 12 becomes the left child of 20. Now I can take 20 as the root node, 10 is its left child and 12 is the right child of 10. Like that. So all these are binary search trees. So here it is possible to draw 5 binary search trees. Out of these 5 binary search trees, which is optimal binary search tree? So what is meant by first optimal binary search tree? A binary search tree, sometimes called as an weight balanced binary tree, which provides the smallest possible search time, which provides a smallest possible search time. That is to be called as binary search tree, optimal binary search tree. Now here you can see the example for that. So here we are given three keys, 1, 2, 3, whose weights are given as 10, 4, 7. So here the weights are given as 10, 4, 7. Now, how to construct the binary search trees using these 3, 1, 2, 3 keys? This is one way. 1 becomes root, 2 becomes its right child, and 3 becomes its right child. This is another way, this is another way, and this is another way, and this is another way. These 5 are the ways to draw a binary search tree using these 3 keys, 1, 2, 3. And if I consider the frequency of those keys, now how to find which is optimal and whose search time is how much search time each one takes. So how to find that one means, here you can see, here 1 is present in the level 1. 1 is present in level 1 and its weight is 10. So that level value is multiplied with its frequency and then we will get this value. 2, the key 2 is present in level 2 and its frequency is 4, which is multiplied with that one. I'll get its value as 8. Now, level 3 is, key 3 is present in level 3 and whose weight is 7. So, when I multiplied the level number with this, I'll get its value as 27. Now, by adding all these 3, so what I will get? 21 plus 8, 29 plus 10, 39 total cost, such cost I will get. Now here 1 into 10, 10. Here this is present in level 2, but its weight is 7. So 2 into 7, 14. And here this is present in level 3, whose weight is 4, 3 into 4, 12. By adding these 3, what I will get? 12 plus 14, 26 plus 10, what I will get? 36. Right. Now, if you see this one, this is in the level 1, whose cost is 4, whose frequency is 4. So, by multiplying level with 4, I'll get this one. This is in level 2, whose frequency is 10, I'll get 20. This is in level 2, whose frequency is 7, I'll get 40. 20 plus 14, 34 plus 4, which I will get as 38. Now, here you can see, this is in level 1, so its value is 7. This is in level 2. Its value is 4 multiplied with that 7, 8. This is in level 3. Its value is 30. Now 8 plus 7, 15 plus 30, which is 45. Such cost is 45. And here I will get 7, 20, 12, 32 plus 7, which I will get its value as 39. Now the search cost for all these 5 trees are 39, 36, 38, 45, and 39. This is the minimum search cost, smallest search cost. This is the smallest search cost, and this is the optimal binary search tree with the given keys and for given probabilities. Right. So this is the general way of finding the optimal binary search tree. So what is optimal binary search tree? An optimal binary search tree is a weight balanced binary search tree which provides the smallest possible search time. Right. So how to find the cost I explained already. This is the smallest possible search cost. So that's why this becomes the optimal binary search tree. So here you given only 3 values, 3 keys. With the 3 keys, I am getting 5 binary search trees. If the number of keys are increased, in that case, I get more number of binary search trees. So in that case, it is not possible simply manually finding the optimal binary search tree. So for that, we are going to develop an algorithm based on dynamic programming. Now let us see what the algorithm that we are taking. So how your problem will be given. So you are given a fixed set of identifiers, let us say A1, A2, A3, A4, AN. These identifiers are nothing but the keys what we are taken earlier, right? The probabilities of 3 nodes are given, and here the values or frequencies. Probabilities are nothing but the frequencies of these 3 nodes. It is given as P1 to Pn, and the dummy node probabilities are also given. Now, what is a dummy node here? Let us see. This is the first node. These are the 2 childs for this. These are the two childs for this, and this is having only one child, let us say, like this it is present. Here there are no any childs. So this is one dummy node, this is another dummy node, this is another dummy node, and this is another dummy node, this is another dummy node, and this is another dummy node, and this is another dummy node. Right. So this doesn't have any children. So these two dummy nodes are present. This doesn't have any children. These two dummy nodes are present. This doesn't have any children. These two dummy nodes are present. This is having only one child. On right side, if it is not having any child, so this is to be called as another dummy node. Suppose your tree contains 6 keys, means 7 dummy nodes are present. So here let us see 1, 2, 3, 4, 5, 6. So dummy nodes are there. 1, 2, 3, 4, 5, 6, 7. That is, if your node contains n keys, if your tree contains n keys, how many dummy nodes are there? N plus 1 dummy nodes are there. Right? Now, the dummy node frequencies are also given, which are from Q0 to Qn. Here you have to observe the things. My keys are A1 to N, that is n keys are there. Probabilities of keys are P1 to Pn, n values are there. Dummy node probabilities are Q0 to Qn. So here these probabilities are n plus 1 probabilities. Why? Because if your tree contains n nodes, it contains n plus 1 dummy node. Right. Now, the optimal binary search tree problem is to construct the optimal binary tree with the given identifiers. So with these identifiers, I need to construct the optimal binary tree. So in the earlier case, what the identifiers here? 1, 2, 3 are the identifiers. Right. In this case, 10, 12, 20 are the identifiers. Like that we given. Right. Now here let us see solving of a problem. So how we solved and how the algorithm is to be considered. So here these represents the steps which are present in the algorithm and how the binary tree is found for the given keys. Now let us see. Here I need to construct this memoization table for optimal binary search tree. Now here I need to take 0 to 4 and here I need to take 0 to 4, right? Since 4 keys are there, I need to take 0 to 4. Now here you can see 0, 0 means W 0, 0, C 0, 0, R 0, 0. Here W represents the weight of the tree, C represents cost of the tree, R represents root of the tree. Right. Coming to here, I will get W11, C11, R11, W22, C22, R22, W33, C33, R33, W44, C44, R44. Now in the same way you can find W01, W02, W03, W04. Right? You can see that 00, 01, 02, 03, 04. In the same way, 11, 12, 13, 14, 21, 22, 22, 23, 24. 33, 34, and 44. These values should be calculated first. Now, for calculating these values, the dynamic programming gives this logic. Now, here you can see how to calculate these values. For I is equal to 0 to n minus 1, we need to find Wi, Wrii, Cii with these formulas. Wi, I plus 1, Ri, I plus 1, Cii, I plus 1 with these formulas. Now, this should be iterated from this path should be iterated from 0 to n minus 1 times, and Wn can be calculated by using these 3 formulas. So up to that we can calculate, we can fill some of the table. Almost upper triangular table will be completed. Now later on we will use this logic to fill the remaining part. So after filling this table, we can go for constructing the binary search tree. Now let us see how we are calculating these values. So here you have given an instance with the identifiers, 4 identifiers. So here your n is equal to 4. 4 identifiers are there. The identifiers are 10, 15, 20, 25, and the probabilities of identifiers are 3, 3, 1, 1. That is the probability of 10 is 3, probability of 15 is 3, and 20 is 1, 25 is 1. Here dummy node probabilities are given as 2, 3, 1, 1, 1. Since your tree contains n nodes, n plus 1 dummy node should be there. So that's why here n plus 1 values. That is 5 values are given for dummy nodes. This is the instance what you given. Now for this, I'm going to solve this instance using this logic, right? Now let us see this one. For I is equal to 0 to n minus 1. N minus 1 means n is 4. N minus 1 means 3. 0 to 3. That is, how many values that I is taking? I is taking 0, 1, 2, 3. 4 values. So first we are taking I is equal to 0. Now here let us see. W00 is equal to, what is this one? Q0. What is this one? Q0. What is Q0 value? It is 2. Right. R00 is 0. C00 is 0. Now here you can see 2, 0, 0. In the same way, I is equal to 1 means W 1, 1. Q1, whose value is 3. Now you can get W11, C11, R11. Right. In the same way, you can get W22, W33, W44 values. Right. So after this, here I have these formulas within the same formula. Now, for I is equal to 0, in addition to W00, I need to calculate W01 as well. W01 is equal to 20 plus Q1 plus P1. Now, what is Q0? 2 plus, what is Q1? 3 plus, what is P1? 3. 3 plus 3, 6 plus 2, 8. W01 is 8. Right? Now, C01. Whatever the value here I will get, the same value I will get for C. Right? Same formula I am using. So that's the same value I will get. C00 is 8. Right? After that, R00 is I plus 1. I is 0 here. I plus 1 means 1. R01 is 1. In the same way, when I is equal to 1, I can calculate W12. When I is equal to 2, I can calculate W23. When I is equal to 3, I can calculate W34. Right? So all these values are calculated. So within this for loop, so what the values I calculated? So I calculated up to these values within this for loop. After this for loop, W44 is calculated, and that is this is calculated. So this part of our algorithm is completed. Right. Now, after this, I need to find this lower part of my table. How to find this lower part of the table? Let us see. For m is equal to 2 to n. That is 2 to 4. How many values that m is taking? 2, 3, 4. Now, for I is equal to 0 to n minus m. That is 0 to 4 minus m, right? So, initially, I am taking m is equal to 2. Now, what becomes I? So, here I take 0 to 4 minus m, right? 0 to 4 minus 2. Here my m is 2. 4 minus 2 means 2. So, how many values that I is having? 0, 1, 2. So, first I am taking I is equal to 0. So, what I am taking? M is equal to 2, I is equal to 0. Now, in this case, what is J? J is equal to I plus M, which is nothing but 2. Right? Now, here what I am finding? Wij. W02. I am finding this value. I am going to find. Now, what is this value? I is 0, J minus 1. J is 2, J minus 1 is 1. Next, here Q2, here P2. Now, already I calculated W01 value. So, here I calculated W01 value, which is nothing but 8 plus Q2. So, here what is the value of Q2? 1 plus here P2. What is the value of P2? 3. Now, what becomes this value? This value entirely becomes 12. That is, I calculated W02 as 12. Now, how to find this value? I know the values of I and J. But what about this K? How to find the K value? Here, now, here we can use this formula for finding K value. Right? That is R I j minus 1 less than or equal to L less than or equal to R I plus 1 j. Right. Now, what is R01? R01 value is 1 less than or equal to L less than or equal to R12. R12 value is 2. Right. Now, L lies between 1 and 2. Means what it indicates is either L is equal to 1 or L is equal to 2. Right. Here, by using this formula, we are calculating L value. By using this formula, we are calculating L value. Now, after finding L value, so here I am getting two L values. One of these L values becomes K. Right. So, K is a value of L. Right. Now, one of these L values becomes K. Then, which L value becomes K? Which minimizes this cost? That is K. Right. Now, for this L value, what is the cost? C, I is 0, L minus 1 is 0, plus C, L is 1, J is 2. Now, we are coming to this L value. C, I is 0, L minus 1 is 1, plus C, L is 2, J is 2. Now, C0 is 0, C0, 0, C00 is 0, and C12 is 7, C01 is 8, plus C22 is 0. Now, I am getting one value. For L, the cost is 7. For this L, the cost is 8. Now, which L value is having minimum cost? This L value is having minimum cost. This L value itself becomes K. That is, K is equal to 1. Now, here you can use that K in this formula to find Cij. Now, this is equal to W02 plus. Now, here K and L both are same. This minimum value that can be directly taken. Right. Now, W02 means 12 plus 7, whose value becomes 19, and here this is the K value, which is nothing but 1. Right, here you can see C02 is 19, R02 is 1. In this way, you can calculate all these values by iterating these two loops. By iterating those two loops, you can calculate all those values. Right. So after finding all these values, how to construct the tree? How to construct the tree? So first we need to take R14 at the root node. Always R14 represents the root node. What is the value of, R04? R04 always represents the root node. What is the value of R04? Its value is 2. Right. Now, since it is 2, its value is 2, the second key becomes the root node. That is, here I am getting 15. Right. Now, when this 10, 20, 25 will be there, that I need to find. So, for that, what I need to take is, I need to consider this formula. I, L minus 1, L, J. I is nothing but here, L is nothing but here, K itself. Right. Or otherwise, I can consider this formula. I, K minus 1, K, J. So, here I is 0, J is 4. Now, I need to take K minus 1 and K between this I and J. So here K minus 1 and K are present between I and J. In the same way we are taking. So here I is 0, J is 4. Now here this is my K value. Is it or not? K value is nothing but Rij. Here R04 is nothing but K value. So K is 2. K minus 1 means 1. K means 2. So this becomes one subtree and this becomes another subtree. So I will get this as 2 nodes. One node R01. One node is R24. One node is R24. Right. Now, how to find the remaining nodes? So what is the value of R01? R01 value is 1. right? Since this value is 1, the first key comes here. This is 10, right? Now, what is R24 value? R24 value is here, it is, this is 3, 4, not 2, 4. Here, this is 3, 4, right? This is 3, 3. So, here, this is 3 means third key comes here. 20 comes here, right? So, if you solve up to this, your problem is over. You can represent that 25 at the right of this 20, or otherwise you can go in the same way, same procedure, right? Now here what the procedure that I can follow? I, k minus 1, k, j. Here my I is 0 and my j is 1 and my k is 1. So k minus 1 is 0, k is 1. So here I am getting 2 dummy nodes. The 2 dummy nodes are R0, 0, R1, 1. Now coming to here, I, k minus 1, k, j. Here I is 2, j is 4, my 2, 4 is 3, k minus 1 is 2 and k is 3. So here I am getting one dummy node R22 and other node I am getting as R34. So here you can see this is R22, this is R34. Here I am getting R34. What is the value of R34? R34 value is 4. That is 4th node. That is 25. So here 25 is coming, right? So you can see 15 root node, 10 its left child, 20 its right child, and 25 its right child. 15, 10, 20, 25. Here you will get the dummy node. Here you will get the dummy node. So this dummy node is R00, this dummy node is R11, this dummy node is R22, this dummy node is R33, and this dummy node is R, right? So this is the optimal binary search tree what we get with the given keys and for the given probabilities. So I hope that you all understood how to find the optimal binary search tree for the given keys using dynamic programming, right? Try to solve by taking one more example with different probabilities and different identifiers. So, thank you for listening. Thank you.